Yeah, as Laura already said, this is not only my work, but rather the work of Pauline Hartwig from the University of Applied Sciences in Wildau. And the idea behind the whole internship, basically, or it rather started earlier with with a student project she did. Unfortunately, she cannot be here today to explain it herself, so it's up to me. Is that it is quite hard actually to just generate demand for SUMO, which is to a point realistic that you have several data points in your small city where you counted, and now you just want SUMO to generate traffic, which resembles these counts. So there are plenty of tools already for a long time. There are several tools. I just copied the screenshot from one of the first SUMO presentations I ever gave. So it is including even the typos I see. And we do not really have, let's say, a very good manual telling people which steps to take to generate their demand if they have this data source, basically, or that data source. So that is not completely our fault. We are focused on micro simulation most of the time and not so much on demand generation. But of course, it's hindering people in using SUMO effectively. So much for the bad news. So the good news is there is an overview white paper, and well, maybe it's even getting a book in preparation now, which tries to solve this. And basically, the idea of the project or the student project, and also of the follow-up internship, was to try this on a small example, at least for the tools which are already in SUMO. So there are also several tools which are not part of SUMO, which can do this. We tried also one or two of these, but the main focus is on SUMO tools. Okay. The small scenario means a small city, and yeah, nobody is surprised. We decided, or they decided rather, on Wildau. The Wildau scenario is quite small, 10,000 inhabitants and 9 square kilometers. You can see here in the picture the city of Berlin, and Wildau is right behind the city borders. We are about, so the DLR is about here, I think. Here is the airport, and so here is Wildau. So you have a direct train connection, you have motorways nearby, and some bus lines in the city, but overall it's quite small, except for the University of Applied Sciences Wildau, of course, which has about 3,700 students. And yeah, let's say this asymmetry between only a few inhabitants and a relatively large educational organization also poses problems in demand generation, of course. But yeah, we'll see later. Okay. So what was the input? The input data was a network generated from OpenStreetMap, the usual starting point for every SUMO scenario, probably. We have a total edge length of about 100 kilometers. So this is here the area covered. That's not all of Wildau. So if you look in OpenStreetMap, then this part of the motorway here in the south is usually also considered to be part of the city, and there's also something more up here. But the students decided to keep it a little bit smaller because that was the part where they have counting data. So the yellow triangles are the places where they have counting data by the city, but there were some major streets which were not covered by the city. So those blue triangles Those are the places where they did additionally manual counts. And if you look at the rectangles here with surrounded edges, those are the traffic analysis zones they tried to define. So they are basically, let's say, rural areas. So they intentionally left out the whole part here near to the train station, which is the university. So they're concentrated on the places where people really live. Okay, the public transport is not that much. I think we have 3 bus lines and 1 train. So this was done manually. And yeah, bike and pedestrian traffic was basically guessed. Okay. And yeah, you can have this whole scenario online in the SUMO scenario repository if you will want to try this yourself. So, okay, how did students start? So they started without any tool, or at least not with the tool I would have chosen, but probably the master tool for every data analysis, which is Excel. No, so they really tried to estimate the routes by hand for every single location on those major routes. They defined which routes could cover the locations, and did this only for the peak hours from 8 to 9 and 1500 to 1600. And after that, did an optimization on that with Excel tools and actually got quite good results, as we will see in the end. But the problem is, first, this process, of course, very cumbersome. So they really did everything by hand. And the other point is you only get traffic on the routes you define, obviously. So your routes you have not in your input will not be covered by vehicles. Okay, so we started from the very other end, so to say, the starting point. So I will now present the tools more or less in the order we tried them out, more or less ordered by increasing, let's say, difficulty of usage. So how much input you need, or how much additional effort you need. And probably the easiest tool, let's say, for everyone is random trips. Of course, you start just a script and generate random input for the whole network. Basically, we adapted only 2 parameters: the generation frequency, so how many vehicles, and a fringe factor, so how many vehicles start on the network border, and that was already quite good. And the improvement was only done further on to increase, let's say, traffic on roads which have larger lengths or a higher number of lanes, but everything was already in random trips, so there was not much fiddling here. Of course, this could not be fitted to the counts directly, because random trips simply does not take counts as input, but it gave a very good network coverage. So that was the first try. And whenever you try random trips, you get some route set as output. And of course, you can try to calibrate this route set just by increasing the counts or decreasing the counts of several routes. So that's basically what Route Sampler does. So it's a calibration tool. We tried the input to use the input of random trips here. And then the Route Sampler does basically an interlinear program on the counting locations and optimizes them. And this, in the end, was even better than the manual fitting they tried. And which was quite surprising in a sense that we did not really put a large effort on the input route set. But on the other hand, was very nice to see that with two, let's say, relatively simple tools, random trips and root sampler, we could also get very good results. Okay, but nevertheless, there was more to be seen. So the next step we did was to try out tools which only take the counts as input. So there's nothing, there's no traffic generated on positions which are not covered by counting data. And so those two tools, the DF router and the flow router, are really generating routes only by distributing the flows, which are originating at some detectors and looking at downstream detectors to find where to direct the flow. So that's what the DF router basically does. The flow router tries to optimize more in the sense of that it solves a maximum flow problem in the whole network, and then increase the flow on certain routes or decrease sometimes, as long as they do not reach the level which is given by the counts. So we did all of this only for the peak hour 1500, but we could reach better results. But of course, the coverage was not so good because we only covered the edges which are covered by counts. Okay. So then we took this in a very different direction. So we tried Saga and random activity again, just to get an idea what we can do if we only take the OpenStreetMap data as input. So we only know where people live and maybe where they work, and what's the daily plan of them is what Saga and random activity again generate. And here we had the nice feature of Saga, for instance, that it also generated public transport schedules. But a big deficiency here was there were no external commutes, so we generated a very low demand. We tried to tweak this a little by just increasing artificially the amount of people living in Wildau, but it did not help a lot. Okay, last but not least, we tried cadets, which is a calibration tool, also external to SUMO, but was already distributed with SUMO for a long time, and should give calibration results, let's say, in the sense of the root sampler, basically. So we also give a root set as input. We have a data set of counts as input. The problem is here that it's a little bit harder to use because you need to convert everything in a separate format. And in our results, unfortunately, it also could not resemble the good results we saw with the root sampler. And now everything you're waiting for is the results. So first, the deviation of the vehicle counts on the counting points. So if you remember, probably you do not, but on the first slide, we showed the counting results in Excel, which were, let's say, about 200 to 250 on average for the counting locations. So if you have an RMSE here on average of over 200, I would consider this basically useless. Let's put it this way. So unfortunately, most of the tools we tried, and I'm not saying the tools are useless, I'm just saying they did not fit our scenario, and maybe we did not try hard enough, but at least random activity again and Saga could not reproduce any of the counts even closely or even remotely, I would want to say, because if you look at random trips, you can see here it managed at least to get the right order of magnitude. It gets at least below the 200, but nothing can beat here in this comparison the manual or the route sampler generated vehicle counts. So they are, let's say, by a large margin, the best tools here to use. But it was not only the only thing we wanted to do here is to fit vehicle counts, because we know it can look strange if vehicles only count there where you count. So we tried to use another measurement, which is network coverage. So which percentage of the routes or of the possible edges for cars were used in the network. And here you see that the network, that the manual routes did already cover more than 80%, let's say, but route sampler and random trips had the same coverage because they used the same basic route set. That's to be expected, but they both got close to 100% here. And many of the other tools did as well. So this is somehow expected, but gives a good idea that the route sampler, let's say best in two measurements here, should be the tool of choice, basically, for at least for the small scenario we tried here. Okay, I'm running out of time. Just a small lookout where this can lead to. We still do not know how we want to do this for public transport or pedestrians or bicycles. And we still do not know really how to estimate what is a plausible route. But we are quite confident that, let's say, at least the first steps are done to give hints to people how to approach those scenarios. Thank you.